Physics part 137. To return to the example of starting a car with its headlights switched on, a large current, perhaps 100 ampere, is supplied to the starter motor by the battery. There will then be a large potential difference across the internal resistance. That is, the lost voltage will be large, the terminal potential difference will drop, and the lights will dim. In the terminology of figure, 7.22 VR is equal to IR and VR is equal to IR, so E is equal to VR plus VR becomes E is equal to IR plus IR, or E is equal to I into R plus R. The maximum current that a power supply can deliver will be when its terminals are short-circuited by a wire of negligible resistance, so that R is equal to 0. In this case, the potential difference across the internal resistance will be equal to the EMF of the cell. The terminal PD is then 0. Warning, do not try. There is a warning for you. Do not try out this experiment as the wires get very hot. There is also a danger of battery exploding. So not advisable at all. Quite often in problems, the internal resistance of a supply is assumed to be negligible, so that the potential difference VR across the load is equal to the EMF of the power supply. Effect of internal resistance on power from a battery. The power delivered by a battery to a variable external load resistance can be investigated using the circuit of the figure 7.24. Reading of the current and potential difference VR across the load are taken for different values of the variable load resistor. The product of VR over VRI gives the power dissipated on the load, and the quotient VR divided by I gives the load resistance R. Well, it shows the variation, the load resistance R of the power of VRI dissipated. The graph indicates that there is a maximum power delivered by the battery at one value of the external resistance. The value is equal to the internal resistance of the battery. A battery delivers maximum power to a circuit when the load resistance of the current is equal to the internal resistance of the battery. We've got an example for you. A high resistance voltmeter reads 13.0 volt when it is connected across the terminals of a battery. The voltmeter reading drops to 12.0 V when the battery delivers a current of 3.0 ampere to a lamp. State the EMF of the battery. Calculate the potential difference across the internal resistance of the lost volt. When the battery is connected to the lamp, calculate the internal resistance of the battery. The EMF is 13.0 volts, since this is the voltmeter reading when the battery is delivering negligible current. Using VR is equal to E minus VR, lost volts are VR is equal to 13.0 minus 12.0 is equal to 1.0 volt. Using VR and IR, R is equal to 1.03. 1.0 over 3.0 is equal to 0.33 omega. Now it's your turn. 3 cells, each of EMF 1.5 volt, are connected in series to a 15 omega light bulb. The current in the circuit is 0.27 ampere. Calculate the internal resistance of each cell. Number 2, a cell of EMF 1.5 omega has an internal resistance of 0.50 omega. Calculate the maximum current it can deliver. Under what circumstances does it deliver the maximum current? Calculate also the maximum power it can deliver to an external load. Under what circumstances does it deliver the maximum power? Well, we'll get along to the summary of this section in our next video as I get to the next one after a while.